this lecture we will find out the area of the green triangle. In the drawing we have a quarter circle. A or B is a quarter circle. Inside the quarter circle we have line segment PQ that is equal to 3 units. Line segment AQ equals to 5 units in its length. And this angle APQ equals to 90 degrees. Our mission is to find out the area of the green right triangle AQO or AOQ. Okay, so first of all, we'll focus on the right triangle APQ, and we will implement on this right yellow triangle APQ the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So the hypotenuse in the right yellow triangle APQ is AQ, therefore the square of the hypotenuse is AQ squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to PQ squared plus AP squared. Repeat again, in the yellow right triangle APQ, according to the Pythagoras theorem, AQ squared equals to PQ squared plus AP squared. AQ equals to 5 units in its length, therefore AQ squared is 5 squared, that is 25. And it is equal to PQ square. PQ is 3, therefore PQ square is 3 squared, that is 9, plus AP square. Repeat again. In the right triangle we found out that 25 equals to 9 plus AP square. Here we will subtract 9 from this equation, and we get that 25 minus 9 is 16. That is equal to AP square. Here we take a root out of this equation and we get that AP equals to the square root of 16, that is 4. AP equals to 4 units in its length. And write it down in the drawing that AP equals to 4 units. AP equals to 4 units. Here we have the quarter circle A or B. You can easily complete the quarter circle to a circle. And then point O will be the center of the circle. Okay, again point O is the center of the circle that we can create by completing the quarter circle to a circle. And we have rule number 2, that a perpendicular from the center of the circle towards any chord bisect the chord. Repeat on rule number 2. According to rule number 2, a perpendicular from the center of a circle towards any chord, bisect the chord. Point O is the center of the circle. From point O, the center of the circle, we draw perpendicular on chord BC. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We defined the touching point of the perpendicular from point O and BC as M. So the perpendicular OM from the center of the circle, that is to say from point O, on chord BC, bisect chord BC. That is to say, divide this into two halves. The first half is BM and the second half is MC. And of course, PM equals to MC. So the perpendicular from the center of a circle towards any chord, here BC could be any chord, the perpendicular from the center of the circle towards any chord, bisect the chord. Again, in this case, BM equals to MC. Okay, so we can implement rule number 2 in our drawing. Why? Because in our drawing, we have the center of the circle is located here at point O. So from the center of the circle, we will draw perpendicular on chord AP. Again, from the center of the circle, that is to say from point O, we will draw perpendicular on AP. So this angle equals to 90 degrees. And this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AP as M. According to rule number 2, the perpendicular OM bisect chord AP. That is to say, it divides it in two halves. AP equals to 4 units in total, therefore the first half PM will be equal to 2 units, and the second half of PA will also equal to 2 units. We define the intersection point between the perpendicular OM and line segment AQ as N. We will define angle PAQ as theta. So in the right small triangle AMN, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees, exactly according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big yellow triangle APQ, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. In the next step, we will prove that the small right yellow triangle AMN is similar to the big yellow right triangle APQ. Okay, so I write it down. Triangle APQ, the big yellow triangle APQ, is similar to the small right yellow triangle AMN. So why those triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So angle APQ, this angle, equals to this angle in the small triangle AMN, small right triangle AMN. Again, they are both equal to 90 degrees, therefore they are equal to each other. I will repeat again. Angle APQ in the big triangle, a big right triangle, equals to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle, angle theta, is a common angle that belongs to both triangles. Therefore, we can say that angle theta equals to itself. From one side, you can define angle theta as angle PAQ. And we call to angle theta another name, MAN. Again, it is a common angle that belongs to both triangles. Therefore, we can say that angle theta equals to itself. I repeat again. Angle PAQ in the big triangle, that is actually angle theta, equals to angle MAN in the small triangle, that is also angle theta, equals to theta. It is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So, yeah, this angle is angle PQA, the big triangle, and it is equal to this angle that is actually angle ANM in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. Repeat again. Angle PQA in the big triangle equals to angle ANM in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually prove that all three angles in the big triangle are correspondingly equal to all the three angles in the small triangle. Therefore, we proved that the two triangles are similar to each other according to angle similarity rule. So I write it down. The big triangle APQ is similar to this is the sign of similar, is similar to the small triangle AMN. According to angle similarity rule. What is angle similarity rule? Angle similarity rule means that if all the angles in one triangle are corresponding equal to all the angles in another triangle, then the two triangles are similar to each other according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will conclude that PA in the big triangle over MA in the small triangle equals to PQ in the big triangle over MN in the small triangle, and it is also equals to QA in the big triangle over NA in the small triangle. I repeat again, from the fact that the two right triangles are similar to each other, we will conclude that PA over MA equals to PQ over MN equals to QA over AN. PA equals to 4 units over MA equals to 2 units, and it is equal to PQ. PQ equals to 3 units over MN. MN is unknown, so we leave it as it is, and it is equal to QA equals to 5 units according to what is given us in the question, over NA that is unknown, so we leave it as it is. So in conclusion, found out that 4 over 2 equals to 3 over MN equals to 5 over AN. That is to say, 4 over 2 equals to 3 over MN. From this equation, we conclude that 4 over 2 equals to 3 over MN. I write it down. 4 over 2 equals to 3 over MN. 4 over 2 is 2, and it is equal to 3 over MN. We'll multiply this equation by MN, and we'll get that 2 times MN equals to 3. Here we'll divide this equation by 2, and finally we'll get that MN equals to 3 over 2, that is 1.5 units. MN equals to 1.5 units. I write it down in the drawing that MN equals to 1.5 units. MN equals to 1.5 units. We can conclude from this equation that 4 over 2 equals to 5 over NA. Okay. 4 over 2 equals to 5 over NA. So 4 over 2 is 2, so 2 equals to 5 over NA. We multiply this equation by NA, and we get that 2 times NA equals to 5. We'll divide this equation by 2, and finally we'll get that NA equals to 5 over 2, that is 2.5 units. NA equals to 2.5 units. So I write it down in the drawing that NA equals to 2.5 units. What is the length of line segment QN? From the drawing it is very easy to see that QN equals to AQ minus AN. Again, AQ minus AN equals to QN. I write it down. QN equals to AQ minus AN. QN equals to AQ minus AN. So QN equals to AQ is 5 minus AN is 2.5. QN equals to 5 minus 2.5, that is 2.5. In conclusion, we found out that QN equals to 2.5 units. QN equals to 2.5 units. I'll write it down. QN equals to 2.5 units. We know that any triangle can be blocked by a circle. I repeat again, any triangle can be blocked by a circle. Therefore, we will block the right green triangle AOQ by a circle. So I copy this right triangle AOQ in a new page, and we'll block it by circle. So actually, this is the right triangle AOQ that I copied from the original drawing. Now we will block this triangle AOQ by a circle. So in this circle, we have peripheral angle AOQ that is equal to 90 degrees. This peripheral angle AOQ equals to 90 degrees. And we have the rule number 5, that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. Again, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. I repeat again rule number 5. Any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. Here, peripheral angle ABC equals to 90 degrees, therefore it must rest on the diameter of the circle. So AC is the diameter of the circle. You see that peripheral angle ABC rests on the diameter AC of this circle. And because of the fact that peripheral angle AOQ equals to 90 degrees, it must rest on the diameter. Therefore AQ is the diameter. According to rule number 5, AQ is the diameter of this circle. But we also know it is given us in the question that AQ equals to 5. AQ equals to 5 units. We know that also the diameter of any circle equals to 2 times the radius. The diameter equals to 2 times the radius. So from this equation, we conclude that 2r equals to 5. 2r equals to 5. We'll divide this equation by 2. And finally we'll get that r equals to 2.5 units. The radius of this circle equals to 2.5 units. Okay. I will copy point N from the original drawing to this drawing. Okay, I will copy point N from the original drawing in our drawing here. So actually, this is point N that I copied from the original drawing. We've already found out that line segment AN equals to 2.5 units. And we also found out that line segment NQ, it is also equals to 2.5 units length. Okay, again, NQ equals to 2.5 and AN also equals to 2.5. But we just right now found out that the radius also equals to 2.5 units. Therefore, ON QA is the diameter. So we have QN that is equal to 2.5, and the radius also equals to 2.5, therefore QN must be the radius of this circle. So QN is the radius that is equal to 2.5, and NA is also the radius that is equal to 2.5. Okay, so we have the diameter AQ that is equal to 2 times the radius, of course, and we have the radius AN and the radius NQ. Point N is the touching point between the two radii, and the touching point between the two radii must be the center of the circle. Very simple. The touching point between the two radii must be the center of the circle. That is to say, point N is the center of the circle. Point N is the center of the circle. Okay, so we join points A and O together by a straight line. What is the definition of line segment NO? Line segment NO starts from the center of the circle, that is to say from point N, and ends at point O, that is the point of the circle itself. This is exactly the definition of a radius. Therefore, NO is the radius of the circle that is equal to 2.5 units. So I write it down here, that NO is the radius of the circle that is equal to 2.5 units. Okay? In the next step, we'll focus on the right triangle AMO. So I'll copy the right triangle AMO in a new page, and we will implement in this right triangle the Pythagoras theorem. MA, side MA equals to 2 units in its length. Side MO equals to MN plus NO. Again, MO equals to MN plus NO. MN equals to 1.5. NO equals to 2.5. So MO in total equals to 1.5 that plus 2.5, that is 4. So MO equals to 4. So actually, this is the right triangle AMO. They call it from the original drawing. The next step, we will implement on this right triangle AMO the Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse is AO squared. Must be equal to the sum of the sides of the perpendiculars, that is to say, it must be equal to MO squared plus MA squared. Okay, again, AO squared equals to MO squared plus MA squared. AO squared equals to MO squared. MO equals to 4, therefore MO squared is 4 squared, that is 16, plus MA squared. MA equals to 2 units, therefore MA squared is 2 squared, that is 4. In conclusion, found out that AO squared equals to 16 plus 4, that is 20. Here we take out of this equation, AO squared equals to 20. AO equals to 20. AO squared equals to 20. Therefore, the square root AO equals to the square root of 20. AO equals to the square root of 20. So I write it down in the drawing that AO equals to the square root of 20 units in its length. In the next step, I will copy the right green triangle AOQ in a new page and we will implement on this right green triangle AOQ the Pythagoras theorem. The hypotenuse AQ equals to 5 units, and we just right now found out that AO equals to square root of 20 units. So actually, I copied the green right triangle AO square here in this page. We'll implement on this right triangle AOQ the Pythagoras theorem. According to the Pythagoras theorem, AQ squared is the square of the hypotenuse equals to AO square plus QO square. Okay, so AQ equals to 5, therefore AQ squared is 5 squared, that is 25, and is equal to AO square. AO is square root of 20, therefore AO square is 20. Square root of 20 square is 20 plus QO square. Okay, 25 plus 20 plus QO square. We subtract 20 from this equation, and you get that 25 minus 20 is 5 equals to QO square. We take a root out of this equation and we get finally that QO equals to the square root of 5 units. QO equals to the square root of 5 units. So I write it down in the following that QO equals to the square root of 5 units. Now it is very easy to find out the radius, the area of the green triangle the green right triangle AOQ. Here, the squared brackets is the sign for the area, so it is the area of triangle AOQ. The area of any triangle equals to the base of the triangle times the height to the base over 2. The height must create 90 degrees is the base. So the base of the green right triangle AOQ is QO. The height is AO. Why? Because AO creates 90 degrees with the base QO. So it is AO over 2. Repeat again. The area of the green triangle AOQ equals to the base of the triangle that is QO times the height to the base that is AO over 2. QO equals to square root of 5 units. AO equals to the square root of 20 units, all divided by 2. Repeat again. QO equals to the square root of 5 units. AO equals to the square root of 20 units over 2. We have the algebraic identity that the square root of A times square root of B equals to the square root of AB. According to this algebraic identity, we get that the square root of 5 times square root of 20 equals to the square root of 5 times 20 divided by 2. 5 times 20 is 100, so in the back, inside the root, we have 100 over 2. The square root of 100 is 10, and 10 over 2 is 5. So we found out that the area of the green right triangle AOQ equals to 5 square units. Repeat again. The area of this green right triangle AOQ equals to 5 square units. In the next step, I'll summarize the lecture. Actually, in this lecture, we found out the area of the green right triangle AOQ. It is given us in the question that line segment AQ equals to 5 units in its length, line segment PQ equals to 4 units in its length, and this angle APQ equals to 90 degrees. Our mission is to find out the area of the green right triangle AOQ. So first of all, we focused on the right yellow triangle AQP, and we implemented in this right yellow triangle the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. The hypotenuse is AQ, therefore the square of the hypotenuse is AQ square, and it must be equal to the sum of the sides of the perpendiculars. That is to say, it must be equal to PQ square plus PA square. Repeat again, in the right yellow triangle APQ, according to the Pythagoras theorem, we get that AQ square equals to PQ square plus AP square. AQ equals to 5 units in its length, therefore AQ square equals to 5 squared, that is 25. PQ equals to 3 units in its length, therefore PQ square equals to 3 squared, that is 9, plus AP square. So 25 equals to 9 plus AP square. We subtracted 9 from this equation and found out that 25 minus 9 is 16 equals to AP square. Here we took a root out of this equation and found out that AP equals to the square root of 16, that is 4. So here AP equals to 4 units in its length. Then we have rule number 2. Here, actually, we found that this is a quarter circle. You can easily complete the quarter circle to a circle, and then point O will be the center of the quarter circle. And we have rule number 2 that says that if from the center of the circle you will draw perpendicular to any chord, it will bisect the chord. Repeat again on rule number 2. A perpendicular from the center of a circle towards any chord, bisect the chord. Point O is the center of the circle. From point O, we drew perpendicular on chord BC. So this angle equals 90 degrees, and this angle equals 90 degrees according to our construction. We define the touching point of the perpendicular from point O and BC as SM. So the perpendicular OM, according to this rule, rule number 2, bisect chord BC. That is to say, divide this into 2 halves. The first half is BM, the second half is MC. And of course, BM equals to MC. So whenever you draw perpendicular from the center of the circle towards any chord, it will bisect the chord. In this case, the perpendicular OM bisects chord BC, that is to say, BM equals to MC. We implemented rule number 2 in our drawing. From the center of this circle, that is to say from point O, we draw perpendicular on chord AP. Again, from the center of the circle, that is to say from point O, we draw perpendicular on AP. So this angle equals 90 degrees, and this angle equals 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AP as M. And according to rule number 2, the perpendicular OM bisects chord PA. and because of the fact that PA in total equals to 4 units, according to rule number 2, OM bisect AP. So the first half will be 2 and the second half will be 2. Okay? In the next step, we defined the touching, the intersection point between perpendicular OM and line segment AQSN. We define this angle as theta. Therefore, if you focus on the right small yellow triangle AMN, this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. Likewise, if you focus on the big right yellow triangle APQ, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Okay? Then we proved that the small right triangle AMN is similar to the big right triangle APQ. So, why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. I repeat again. Angle APQ in this big triangle equals to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle theta is a common angle that belongs to both triangles. Therefore, angle theta equals to itself. Okay? And angle theta equals to itself, it's a common angle. So we call to angle theta two different names. Angle theta is actually angle PAQ, and it is equal to itself. It is equal to angle MAN, that is also angle theta. They are both equal to theta, so it's a common angle. Angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. Repeat again. Angle PQA in the big triangle is equal to angle A and M in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we proved that all three angles in the big right triangle are correspondingly equal to all the three angles in the small triangle. Therefore, the two triangles are similar to each other according to angle similarity rule. Again, the big triangle APQ is similar to the small triangle of AMN. This is the sign of similar. And are similar to each other according to angle similarity rule. What is angle similarity rule? Angle similarity rule is that if all the angles in one triangle are correspondingly equal to all the angles in another triangle, then the two triangles are similar to each other according to angle similarity rule. Because of the fact that the two triangles are similar to each other, we will conclude that AP in the big triangle over AM in the small triangle equals to PQ in the big triangle over MN in the small triangle, and it is also equals to AQ in the big triangle over AN in the small triangle. I'll repeat again. PA over MA equals to PQ over MN equals to QA over AN. PA is 4, MA is 2, PQ is 3, MN is unknown, QA is 5, and NA is unknown. So conclusion found that 4 over 2 equals to 3 over MN equals to 5 over AN. From this equation we can conclude that 4 over 2 equals to 3 over MN, 4 over 2 equals to 3 over mn. 4 over 2 is 2, so 2 equals to 3 over mn. We multiply this equation by mn and found out that 2 times mn equals to 3. Then we divided this equation by 2, and finally we got that mn equals to 3 over 2, that is 1.5 units. Here, mn equals to 1.5 units. We can conclude from this equation that 4 over 2 equals to 5 over mn. Again, 4 over 2 equals to 5 over na. Okay. So 4 over 2 equals to 5 over na. 4 over 2 is 2, so 2 equals to 5 over na. We multiply this equation by na, and finally we found out that 2 times na equals to 5. We divided this equation by 2 and found out that na equals to 5 over 2, that is 2.5. Here, na, line segment na equals to 2.5 units in its length. What is the length of line segment NQ? From the drawing it is very easy to see that NQ equals to AQ minus AN. AQ minus AN equals to NQ, very simple. I'll repeat again. NQ equals to AQ minus AN. So NQ equals to AQ, that is 5, minus NA, that is 2.5. So NQ equals to 5 minus 2.5, that is 2.5. In conclusion, found out that the length of line segment QN is 2.5 units. The length of this line segment QN equals to 2.5 units. We know that any triangle can be blocked by a circle. Again, any triangle can be blocked by a circle. Therefore, we can block the right green triangle AOQ by a circle. So I copy the right triangle AOQ in this new page, and we blocked it by a circle. So inside this circle we have peripheral angle AOQ that is equal to 90 degrees. And according to rule number 5, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. Repeat again. Any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. Here, peripheral angle ABC equals to 90 degrees, therefore it rests on the diameter of the circle. So AC is the diameter of the circle. Okay? So, and because of the fact that peripheral angle AOQ equals to 90 degrees, it must rest on the diameter. Peripheral angle AOQ rests on AQ, therefore AQ is the diameter of the circle. Very simple. AQ is the diameter of the circle. So we wrote it down that AQ is the diameter of the circle. But it is given as the equation that AQ equals to 5 units from one side. From the other side, we know that the diameter of any circle is twice as long as the radius. So the diameter equals to 2 times the radius. 2 times r. R is the radius. And from this equation, we will conclude that 5 equals to 2r, or 2r equals to 5. We divided this equation by 2 and found out that r equals to 2.5 units. So the radius of this circle equals to 2.5 units. Then I copied point N from the original drawing to this drawing. This is point N that I copied from the original drawing. We have already found out that AN equals to 2.5. Here AN equals to 2.5 units. And also NQ equals to 5 units. NQ also equals to 2.5 units. Okay, so NQ equals to 2.5 and AN equals to 2.5. And we also know that AQ is the diameter of the circle. And the radius of the circle is 2.5 units. And because of the fact that AN is part of the diameter and NQ is also part of the diameter, and AN equals to 2.5 and the radius of the circle also equals to 2.5, we conclude that AN is the radius of the circle, and also NQ also equals to 2.5, but NQ is the also the radius of the circle equals to 2.5. So NQ must be the radius of the circle. Okay, so we have the diameter AQ. On the diameter AQ, we have the radius of AN and we have the radius NQ. Okay, we have the two radii on the diameter of the circle AQ. So the touching point between the two radii, it occurs at point N. The touching point between the two radii must be the center of the circle. Very simple. If you have diameter of any circle, then the touching point between the two radii must be the center of the circle. That is to say, point N is the center of the circle. Point N is the center of the circle. We join points N and O together by a straight line. What is the definition of line segment NO? Line segment NO starts from point N, that is the center of the circle, and ends at point O, that is a point on the circle itself. This is exactly the definition of a radius. So NO is the radius of the circle, that is equal to 2.5 units. So here NO is the radius of the circle, that is equal to 2.5 units. In the next step, we copied the right triangle AMO in the new page and we implemented in this right triangle the Pythagoras theorem. Side AM equals to 2 points in its length, 2 units in its length. Side MO equals to MN plus NO. MO equals to MN plus NO, MN equals to 1.5 and NO equals to 2.5. Therefore, in total, MO must be equal to 1.5, that is 1.5 plus 2.5, that is 4. MO equals to 4. So actually, this is the right triangle AMO that I copied from the original drawing. We implemented on this right triangle AMO the Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse AO square must be equal to MO square plus MA square. Again, AO square equals to MO square plus MA square. AO square equals to MO square. MO is 4, therefore MO square is 4 square, that is 16, plus AM square. AM is 2, therefore AM square is 2 square, that is 4. So AO square equals to 16 plus 4 is 20. AO square equals to 20, we took out of this equation and finally we found out that AO equals to the square root of 20 units. Here, AO equals to the square root of 20 units. Then we implemented the Pythagoras theorem on the right green triangle AOQ. So I call it the right green triangle AOQ in this new page and we implemented on it the Pythagoras theorem. AQ equals to 5 units according to what is given as the equation. Then AO equals to the square root of 20 units according to what we have already found out. So according to the Pythagoras theorem, in this right triangle AQO, AO square equals to AQ square equals to AO square plus QO square. Again, AQ square equals to AO square plus QO square. AQ square equals to AO square plus QO square. So AQ equals to 5, therefore AQ square is 5 square, that is 25. And it is equal to AO square. AO is square root of 20, therefore AO square is square root of 20 square, that is 20 plus QO square. 25 equals to 20 plus QO square. We subtracted 20 from this equation, 25 minus 5 is 5, so 5 equals to QO square. We took out of this equation and finally we found out that QO equals to the square root of 5 units. QO equals to the square root of 5 units. Now it is very easy to find out the area of the green right triangle AOQ. Here, this is the sign of the area. The square bracket is the sign for the area. It means that the area of triangle AOQ equals the area of any triangle equals to the base of the triangle times the height to the base over 2. The height must create 90 degrees with the base. So the base is QO and the height is AO. Why? Because AO creates 90 degrees with the base QO. So it is QO times AO over 2. again, the base is QO, the height is AO over 2. QO equals to the square root of 20, QO equals to the square root of 5 units, AO equals to the square root of 20 units, all divided by 2. QO equals to the square root of 5 units, AO equals to the square root of 20 units, all divided by 2. We have the algebraic identity that the square root of A times square root of B equals to the square root of AB. Therefore, according to this algebraic identity, we'll get that the square root of 5 times square root of 20 equals to the square root of 5 times 20 over 2. 5 times 20 is 100. So inside the root, we're left with 100 over 2. The square root of 100 is 10, and 10 over 2 is 5. So finally found out that the area of this green right triangle AOQ equals to 5 square units. Again, the area of the green right triangle AOQ equals to 5 square units in its length. Okay, thank you very much.